This is a difference amplifier. This thing here where we have negative feedback, and if we look at the input 1, we can understand its gain through here. If we zero out this input 2 and just look at input 1, we can see the output of it, and that's an inverting configuration. If we've got 0 here, then we have 0 on this node because we have 0 everywhere. We have 0 on this node. It's simply an inverting configuration, minus R2 over R1. On this side, we have, if we zero out VI1 and look at VI2, then we've got ground right here. And that means we have the non-inverting configuration. And the non-inverting configuration has a gain of 1 plus R2 over R1. And we're trying to make a difference amplifier. And to amplify the difference, we'd like to have VI1 and VI2 amplifying at the same amount and subtract them. So we use this extra divider here, R3 over R4, to divide down VI2 so that the end result is on VI2 we have a plus R2 over R1 kind of gain. And that will occur if we set the resistor ratios to be R4 over R3 is equal to R2 over R1. And if we do that, we'll get a differential gain of R2 over R1. Differential gain means the gain for the difference between this input and this input. If we subtract this from this, we'll have a signal. Say if this was plus 0.1 and this is minus 0.1, we have a difference of 0.2. And then if we have a differential gain of 10, we have 0.2 times 10, then we'd have 2 volts on the output. That's what we mean when we say we have a differential gain there. So, and that depends on having that ratio, that magic ratio of R4 over R3 equal to R2 over R1. But there's also the question of what happens with the common mode signal, just like that noise I showed from the on the AD-ALM 2000. So if we're looking to understand common mode noise, I don't know what's going on there. Oh, come on. All right. Just redraw the circuit quick there. And what we're saying is that we're going to connect those two inputs together and apply a common signal to the two of them. So if we're looking for the common mode gain, we need to tie the inputs together. And then we apply VICM, the common mode gain. And we've got R3 and R4, 2 and R1, and V out. So, and we're looking to find out what that that gain is from V out all the way back to VICM. So the common mode gain will be ACM is equal to V out over VICM. That's what we're looking for, is to find that combination gain of all those. So we still have a virtual short. Whenever you have negative feedback, you can always draw that virtual short in. It'll help you understand what's going on. So that means whatever voltage we have on the non-inverting pin, we're going to have that same voltage on the inverting pin. So the virtual short means that V plus is equal to V minus. And It might be hard to figure out what V minus is, but V plus is easy. We've got a voltage here, VICM, applied through a divider. So V plus is a divided ratio from VICM. And our goal, in order to make to find the gain, we always want to have an equation V out on one side and VICM on the other side, and we'll find out what that ACM is actually equal to. So we have a current. We can say we've got a current I1, and that's going to equal I2. So I've drawn them that way. And VI1 is going to be the difference from this node here, which is VICM, over to this. So the difference between these two voltages divided by this resistance R1 will get us that current I1. And that current I1 is flowing through R2. So then once we know this voltage, we can find that current. Once we know that current, then we can find the voltage over here because the current here is the same as that current there. So I1 is equal to VICM, that equals V minus. So V plus is equal to V minus. So VICM minus V minus, the inverting pin voltage, over R1, call it V plus. And that's going to equal, V plus is that divider, so VICM minus R4 over R4 I've got a dumb little dongle up in my office, but this will just take a minute to charge, I think. Here, VIC, what we want to find is this voltage here. That's this voltage here. So we've got VICM through this divider. It doesn't want to work. It'll charge up probably very quickly. I probably have to pair it before I finish doing anything. So we're going to have that divider, and I'll write it out in a minute here. I wonder how long I should wait. If I've got a 1 over R1, so I need to have that there. So we have something like that, and we could do some algebra and write that as VICM R1 times R4 plus R3 over R4 plus R3. That's the same as 1 minus R4 over R4 plus 3 and we're subtracting out an R4 there, so those go away. Then we have VICM over R1 times R3 over R4 plus R3. That equals I2 as well as I1. And so from that, we can get the output voltage, which is V minus the inverting node voltage. So that difference between them and the current in the voltage gives us that. So VI inverting pin minus I2 R2, which would be the same as V plus minus I2 R2 which is equal to R4 over R4 plus R3 times VICM minus VICM times R2 over R1 R3 over R4 plus R3. And we can rewrite that and get rid of some more stuff. So we have R4 plus R3 times VICM minus VICM times R4 plus R3 times R2 over R1 times R4 plus R3 over R4 times R3 over R4 plus R3. By doing that, we can cancel those. And we're going to get V out is equal to VICM R4 over R4 plus R3 times 1 minus R2 over R1, R3 over R4. And what we're looking for is V out over VICM. If we can do that ratio, then we found ACM, common mode gain. So we get a common mode gain of R4 over R3 plus R4 plus R3 times 1 minus R2 over R1 times R3 over R4. And if, again, R2 is equal to R4 and R1 is equal to R3, then we have some canceling, and we have, this is equal then to R2 over R2 plus R1 times 0, because this quantity here will become 1, so 1 minus 1 is 0, and equals 0. So it will reduce to a common mode gain of 0, which would be wonderful. That's what we want. If the common mode gain is 0, then it perfectly, absolutely 100% rejects any common mode signal. So that common mode signal I showed before, if we have a common mode gain of 0, none of that common mode signal would go through. It's all completely gone in this difference amplifier, which is great. Reality isn't quite that good. So any mismatch between those transistors, so if R2 doesn't perfectly equal R4 or R1 doesn't perfectly equal R3, then the common mode gain is not going to be 0. It would be something other than that. And it could actually be quite bad, right? In real life, it wouldn't be anywhere near as sweet and nice as being a common mode gain of 0. Note that the CMRR, the common mode rejection ratio, is 20 log of the differential gain over the common mode gain, and that equals 0 for infinite if ACM is equal to 0, right? That it works out to be wonderful, an infinite common mode rejection ratio if it's 0. Now, I've told you with amplifiers in general, we're always interested in 3 things. If we can understand the gain, and so now we've got the differential gain, the common mode gain, so we've got the gain of this amplifier, this difference amplifier. And if we can understand the output resistance and the input resistance, then we can actually model this as an arbitrary amplifier. We don't need to try and understand any details about what's happening inside of it if we know the input resistance, the output resistance, and the gain. So we really want to know the input resistance of this differential amplifier. So if I redraw it, we've got a difference amplifier That lovely sound stopped, so maybe we're okay. So what we're really trying to find is what does this differential input source C as a resistance. So what is the resistance looking in the input differential resistance? We always want Rn, Rout. And we're looking for a special Rn here because we've got a differential signal that we're applying. So so we always have this virtual short. It's always existing between the non-inverting and the inverting pins. You've always got that there. And a input resistance Rn is equal to Vn over In. We can find the input current and the input voltage, then we can divide those to find the input resistance of this amplifier. So here we're looking for RID, so the input differential current with this differential voltage source. So we're really looking for RID is equal to VID over IN. That's what we're really looking for in this case. So the virtual short makes it seem as if the inverting pin is, well, it does make it so the inverting pin is exactly the same voltage as the non-inverting pin. And so we can solve it looking that way. We can look at so we could look at it as if it's that circuit, as if there's a connection there. We're not really talking about current flowing through there. There's not actual current flowing through there, but it's as if we could say there is a current loop there because they're essentially connected, right? So just as if I have a circuit like this, and I have two grounds right there, these are at the same voltage, and we don't actually know if there's any current, but we can solve for a loop around here because these two nodes are at the same voltage. But it doesn't really mean that there's any current flowing between there. So, but we could, and if we have, if R3 is equal to R1, which we've said we want, then it's basically like we've got two R1s in a loop with a VID, and so then VID is equal to the input current times 2R1, because we've got a current there. Draw it that way. Or RID, which is equal to VID over IN, would be 2R1. So the input differential resistance is not much better than the inverting configuration. And actually that might make some vague sense to you because this amplifier is half of an inverting configuration, and the other half is the non-inverting configuration. And so we've got a input resistance due to R1 and another R1, which is the same value, of 2 times R1, which is not a high input resistance. That's actually a really big problem. We always want to have a high input resistance, and the nice thing about the non-inverting configuration, it has an infinite input resistance, but this difference amplifier doesn't. There's another problem with this amplifier, and that is if we want to change the gain, we've got to change 2 resistors. We've got to change R1 and R3, R2 and R4. We've got to change a pair of resistors, and that's really hard to do. If I told you that you have to change those difference pots on that bipolar supply exactly the same amount, you'd probably really be unhappy with me. I said you should get plus or minus 10 millivolts, but some of you had plus 60, minus 40. I say, oh yeah, that's fine, because it's hard to set those exactly the same. And it's hard to have exactly the power supplies the same. So changing the gain of this amplifier would require adjusting 2 resistors at least. And another way of looking at that is if your resistors are unstable for some reason, or you buy slightly different resistors, that will change the gain, and it would be unfortunate. It could also change the common mode gain. So a scheme called the instrumentation amplifier fixes all that and more. It uses some more op amps, but if we put a buffer on this input here and a buffer on this input here, then we can have high input resistance. And we get some other advantages if we make them. So what I'm saying is if we build, if we've got this difference amplifier, so it's a difference amplifier, but then on the inputs, we put a buffer so that, leave myself much room, make some more room. If we add a couple of buffers like that, then we now have high input resistance. So whereas in this case, we had an input resistance, a differential input resistance of just 2R1. If we put a couple of buffers on the inputs, now looking into each of these op amps, we have infinite input resistance. There is no current going into that amplifier. Right? There's no current going into that those buffers, which means that there's no that there's an open circuit as far as input resistance. But you know, as long as we're going to all the trouble to put a buffer here with negative feedback, we might as well make a non-inverting configuration, and we can get some gain there. Just put in a couple of resistors here and a couple of resistors here. We have non-inverting configuration. It still has infinite input resistance, and now we get some gain on these input stages. And then we also have a difference amplifier there. You know, might as well do that. So if we're going to do that, I'll try to leave myself more space this time. Oof, that doesn't look like a triangle at all. So we've got a basic difference amplifier here. And then said we want to have the non-inverting configuration. So we'd have an input going to the non-inverting pin, and hopefully that'll be clear the way I'm drawing it. There's okay, so so we've got resistors. We've got, call this R4, R3, R3, R4. We have V out. We have a VI1 and a VI2, and we have R2 and R1. So now we've got, so I took this buffer configuration right here. It has a gain of 1, right? We have exactly the same voltage here or here as we have here, and just change it to the non-converting configuration, right? And I've got these two op amps switched, so I've got the minus on the top here, and I got the minus in the bottom here, just so it kind of draws nicely. But we've got negative feedback here, and we've got negative feedback here. So this is a non-inverting amplifier, and this is another non-inverting amplifier. And we've got both these, the inverting side, we've got both of these connected to ground, right? So that is, I mean, that's exactly what we want, but we might as well actually just connect these two nodes because they are, right? They're exactly the same thing. So I could redraw it one more time, and so we have VI1, VI2, at R2, R1, R1, R2, 4, 3, 3. You need to make one more connection there. R4, V out. And I have to have ground there. So all I did really was slide these two resistors R1. They used to be down here, and I slid them up this way. If you look at this, this is exactly the same. I just slid R1 kind of vertically, these two R1s, and made a connection to ground in between them. It's the same circuit. And and we might as well call this node, we'll give it a name, X. That node between there, it's at ground, but we could call that node X. So now, and we could say that we have a stage, call this A1, A2, A3. And so these first stages, A1 and A2, so that first stage, they're both non-inverting. The gain is just 1 plus R2 over R1. And we could make that a big number, right? And the inputs here to this difference amplifier are the outputs of these non-inverting amplifiers, right? So the second stage inputs we have 1 plus R2 over R1 times VI1 and 1 plus R2 over R1 times VI2. Those are the inputs to the second stage. And if we think about that as a difference amplifier, it has an input of 1 plus R2 over R1 VID, because that is 1 plus R2 over R1 times VI2 minus VI1. Right? That's what we're actually giving it. Right? We're giving them it's doing the difference of those. And the gain of a difference amplifier like that is just R2 over R1 that we got by superposition. So then and in this case R2 and R1 is now called R4 and R3. So V out is equal to R4 over R3 times 1 plus R2 over R1 times VID. Or the differential gain is V out over VID, which is equal to R4 over R3 times 1 plus R2 over R1. And the common mode gain is equal to 0. So we took care of that input resistance problem. We now have an infinite input resistance, which is good. We still have a common mode gain of 0 because that's what the difference amplifier over here does. So any common mode, how do I do that? Yeah. Any common mode signal is completely rejected. But this first stage right here will amplify common mode signals, right? So So this one perfectly eliminates common mode signals, but this one's going to amplify them, which makes it harder for this one to work. And like I say, if there's any mismatch between these resistors, we will actually have some common mode gain. Yeah. So we have to, if there's a common mode signal here, this amplifier amplifies it. Any signal on this input will get amplified to here. So if there's a common 2 volts, it's amplified to here. We've got a gain of 2 or 10, then we've got a 20 volt signal here. And if we have a common mode signal here of 2 volts, then it becomes 20 volts over here. Those differential signal, or the common mode signals, are perfectly amplified to here, although this difference amplifier is supposed to get rid of them. Ideally it will, but we know if there's any mismatch between these resistors, then it will have some trouble with doing that. And we have an additional difficulty now because if there's any mismatch between these R2 over R1s, if this R2 over R1 is a little bigger than this one, then we're going to make a little bit bigger signal here than down here, which is a problem. So it's kind of you know, 1 step up and 2 steps backwards or something, right? We've gained some things, but we've also lost some things, or we haven't gathered some advantages, and we still have trouble changing the gain. We still have to change a pair of resistors somewhere. We could change both R2s, but we'd have to change both R2s by the same amount to make the gain work correctly. But there's a evil fix to make this circuit much better. It has a dramatic impact, and that is remove this ground. So if we remove this ground, this whole circuit becomes much, much better behaved, and things will work nicely. In fact, there is a current flowing through here to ground, and there's a current flowing through to here to ground, and it could be this current is going this way and this one's going this way. We don't really know which way those currents are necessarily, unless we figure it out. But if we remove this, it just says that this current is going to flow through here, right? We're just going to share the current. And by sharing the current, we get rid of a whole bunch of problems. Basically, we're going to be relying on the virtual short that exists here, and the virtual short exists here to improve the performance. So let me draw that. So all I've done between this circuit is get rid of that connection to ground there. We still have a node X right there, but we've got 2 resistors in series, R1 and R1. So I might as well just call this new resistor 2R2 or 2R1. So now, if we wanted to analyze this, remember everywhere we've got negative feedback, we've got a virtual short. And I can ignore this part for a while. This is just a difference amplifier, which we already did. So the real question is what's going on in this crazy combination of stuff right there. So we've got a current. We've got a current that's flowing around. And we call that current I if we want. That current, the main thing is that that current is flowing through both R2, 2R1, and this other R2. That same current is flowing through all of them. And because of that virtual short, so we got the non-inverting and the inverting, got the inverting and the non-inverting. Because of these virtual shorts, that means that, for instance, VI1 shows up on this node. So we really have VI1 right there. In a similar way, because of this virtual short, then we have VI2 showing up here. And so now we have VID showing up between, I'm not sure if I got those pluses in the right spot. We got the input differential voltage showing up across this resistor 2R1. And VID, I'm almost sure I've got those pluses wrong. Just yeah. I think it should be like that. So VID is equal to VI2 minus VI1. And that exists in there across that 2R1. Each of these has an output voltage. We have an output voltage of V out 1 here and V out 2 there. And the output voltage, if we know the current in here and we know this voltage here, so we know the current in this R2 and we know the voltage here, we know this current, then we know the voltage drop across this resistor, then we know that output voltage. And by the same means, if we know this voltage here and we know the current flowing through here, we know the drop in this resistor, then we know V out 2. And we also know that we've got this voltage V out 1 here and a voltage V out 2 here, and there's the same current flowing through all of these, that we have a series resistance of R2 to R1 and R2, which is the voltage drop between these two. All right, so we can say that difference in outputs, V out 2 minus V out 1, is equal to R2 plus 2R1 plus R2 times VID over 2R1. So the current in here is VID. That current is VID over 2R1 because VID is the difference here. That's that current. And if we multiply that current by this series resistance, then we get the difference between these outputs. And this simplifies, or we have then 2R2 plus 2R1 over 2R1 times VID, and that equals 1 plus, I should have written those the other way, but we've got, so that's a 2. 1 plus 2R2 over 2R1 times VID, just to keep those 2's in there for crazy. And that's the difference, or that's the input to the difference amplifier, right? The output voltage here, the difference between these output voltage is actually the difference right here. That's the input value to this difference amplifier, which has a gain of R4 over R3. So the total output, V out, is R4 over R3 times V out 2 minus V out 1. That's its inputs, which is equal to R4 over R3 times 1 plus 2R2 over 2R1. And so these are different resistors, right? We still have to worry about mismatch, perhaps, of these resistors. Yes. Yes. Thank you. I was really writing it as the gain. Let me write it as the gain. So if there's some mismatch between these, And we might call this R prime 2, and we might call this R double prime 2. There's no undo in this mode. It's not really an arrow. So there could be a mismatch between these R2s, and we could call them R prime 2 and R double prime 2. So call that prime and double prime. Then the differential gain is equal to R4 over R3 times R2 prime plus R2 double prime over 2R1. That means there's not really any mismatch because the same current is flowing through these two resistors, right? We haven't actually changed anything. It looks like 2R2 might have a mismatch if these two are different values, but in fact, if they're different values, they sum up to some number over 2R1. It'll change the gain of the entire amplifier, but it won't change the differential gain if these two values are actually different. If they're not the same R2 value, it won't change the differential gain. Well, it'll change the differential gain, but it won't cause a mismatch between the sides, which is what we'd be worried about. Now, if there's a common mode input, if we have 2 volts here and 2 volts here, that means we have 2 volts here and we have 2 volts here, and it's trying to reject it. So in fact, it'll still flow through, but it won't be amplified. That common mode gain won't be amplified. We'd still have that 2 out here, but it won't be amplified. So the first stage does not amplify the common mode, but it amplifies the differential signal. And then the second stage can further reject the common mode signal without and amplify the difference. And we can change the gain of this entire system by just changing the gain of R1. We can change it by changing either the R2s, but if we just change R1, then we've changed the gain of this whole system. So we got one knob, like one volume knob, we can turn the gain up and down. So that's much easier than the other way. We've got a high input resistance going in for both the inputs, so we've got that advantage. We don't have any more problem with mismatch between R2 and R1. We do still have the problem of mismatches between R3 and R4, and they'll cause, if they cause a differential gain problem, we can just adjust R1 if we have a pot there. But they will cause a common mode gain. But the good news is that the common mode, relative to the difference, is much less. And so this amplifier is a wonderful improvement. It's called an instrumentation amplifier, and they're common. They're all over the place. I'm sure they're in this room. In fact, I'm sure you all have a bunch of them. So they're wonderful for amplifying any kind of signal and rejecting noise. So for sensors and things like that, they're wonderful, but they can work for antennas. They can work for little wimpy pin outputs. They can work for all kinds of things. And your watches, just all kinds of stuff. They're all over the place. They're really simple. They're robust. You can make an integrated circuit version, but you can also buy ones that are standalone. And in fact, your kit your parts kit, the AD-ALP2000, has a very nice instrumentation amplifier, and we will start using it in labs.